welcome to an educational segment of You Got Potential. Today we're going to cover machine learning and its connection with the behavioral and neurosciences. This is an extremely interesting topic. If you guys are a CBN major or a neuroscience major, you're definitely going to want to hear about this. Especially since maybe you join the major not knowing that there are super computationally oriented fields of research within neuroscience and behavioral sciences or social sciences. And so I hope that you guys get a lot out of this presentation. So first of all, what exactly is machine learning? Well, what I'll tell you what it isn't. It's not like the Terminator from the 80s, and it's not necessarily Elon Musk's Neuralink or these crazy buzzwords and technologies that you hear about, although they're very related. But quite simply, it's when a computer improves its accuracy or efficacy at completing a certain task without explicit programming or additional programming from a human or human intervention. And so this is just revolutionary because progress could be made exponentially toward trying to model something or predict something without the need of massive amounts of manpower. And so you'll hear a lot about job replacement and things like that because of machine learning. And that's for that exact reason. But it can be extremely accurate, and it could be a very useful tool in elucidating mechanism of action or just finding correlations that you haven't seen before. It's very important in empiricism. And so first, we're going to talk about the three types of machine learning. So there's reinforcement learning, supervised machine learning, and unsupervised learning. So reinforcement learning is sort of like when you're training your dog and you give it a treat when it does something that you want. The machine is rewarded, right, or it's told positively that, look, doing this action is good, and it'll do more of that, or it'll do it more efficiently, or it'll do that in conjunction with other actions and see if it can get additional reward. Basically, you're sort of leading it to the desired output using some sort of reward. Supervised machine learning is very interesting, and it's basically you give a bunch of input data, right, and then you give it a bunch of output data, and you let the machine learning algorithm figure out the relationship between the input and output x and y, and then you give it a new input with an unknown output, and you ask, hey, can you figure out what the output is? So for example, right, let's say you wanted to figure out the diagnoses of a certain MRI image, right? You can give it 1,000 images diagnosed by a radiologist saying, hey, this person got a brain tumor or something like that. And then it could start to break down the image and find what are the structures of this image or the brain that are associated with certain clinical outcomes. And then you can use that going forward if you have a good enough training set to figure out, okay, without a radiologist potentially, although, that's an ethical issue. Does this person have a tumor or not? Or do they likely have a tumor or not? And then so finally we have unsupervised learning. And this is extremely interesting, right? So this is when the machine can categorize data based on similarities within data points, right? So let's say you gave the machine, again, we'll go with a brain example. So hundreds of images of brains, right? But these are brains of monkeys, chimpanzees, and gorillas. And you want to know the differences between their brain structures because to the untrained eye, they may look all the same. But machine learning algorithms can actually find structures that are unique to a group of data points and then categorize and ascribe a label to them. So maybe it'll find that gorillas, they really tend to have this brain structure. This specific structure is unique to gorillas. And so all data points with this structure belongs to gorillas or chimps or humans. And so you can see how already in the behavioral and neurosciences that machine learning is extremely applicable and very, very useful. This is part of deep learning, and it's called neural networks. And I want to go over this because there's a lot of analogies that can be made between neural networks and how the brain processes sensory information. For example, so let's say you see a dog, right? And so like you've seen tons of dogs, but how do you know the differences between all these dogs, right? Dogs have a general shape. They all have a general features that are ascribed to be what's called a dog, but then there are different breeds of dogs and sizes of dogs, and yet you still know it's a dog. How does your visual cortex or your occipital lobe actually do that? How is the decision making done? Well, in computers, it's done through neural networks. So you have this input on the left here, right? And you have an output on the right. Your output is your answer, and your input is your question, right? And so then you have these layers in the middle, these columns. There's usually more than one column, and it's called a hidden variable. And so what these hidden variables do is they actually sequentially layer and build the image, the output, from the ground up. So imagine um, all the pixels that are in this picture, right? Let's say there's 1,000 pixels in this picture. There's probably more, but let's just say, for sake of argument, there's 1,000 pixels, right? Each of these pixels has what? Has a color, a shade, a tone ascribed to it, right? So you input this picture, and then these lines shoot off to stuff that correspond with your input. So these lines would shoot off to all the different pixels, right, that line up with the input. And these pixels are defined by numbers, right? So color is defined by numbers. So if it's brown, for example, let's say brown is represented by 1, black by 2, white or gray by 3. So each of these pixels have a number ascribed to it. And then, well, there's other things to this image, right? Well, there's also the shape of its ears, for example, right? So then each of those pixel colors will shoot off into directions, and those will be ascribed to ears, right? The specific shape of the ear that you have to define. And then slowly from ears, you go to head structure, skull structure, and then to eye structure and nose structure, and you can start to piece together, just based on the colors and the pixels, right, what the output is going to look like. And then you figure out, okay, this is the final image, and it's this type of dog. And neural networks sort of work analogously to how our brain thinks. I'm going to get to that in a second. And so here I just have in writing what I basically just said, right? Where these outputs are mapped to inputs, or rather vice versa. Inputs are mapped to outputs. And this mapping, right, this relationship between X and Y is done by a machine learning algorithm. What I want to say, another comment I want to say is that the more input data that you feed it when you're training it, right? So think supervised learning, right? You have a training set that maps an X to Y. Neural networks and supervised learning are not exactly the same thing, but for these purposes, I want to use them together in conjunction with one another. The more training set data you have in your supervised learning, so the more different angles that you've seen this image at, the more different specific individuals of dogs, because there's variation, right, even within breeds, the better your training set is going to be in terms of prediction accuracy. Or perhaps not. It's actually possible not, right? Maybe there's cross-individual or cross-species analogous or homologous traits that result in statistical error, right? And so this is where machine learning algorithm design and engineering comes into play. So here I'm showing about sort of an analogy of how neural networks and the brain work. So here's your eye with a blow up of how the retina is structured, right? So you have this retina that's got cones and rods which cover color and sort of visual acuity and detail. So the light is transmitted in there, right? Picked up by the rods and cones. It's synapsed with the bipolar cells, and then the bipolar cells are subsequently synapsed with your ganglion cells, and these ganglion cells then bunch together into a nerve, which is sometimes called the blind spot, right? And that nerve is hooked up into your occipital lobe, or your visual cortex, and the visual cortex and the parts of the brain is where the magic happens, right? This is where your neural network is going on. So you've received this image. How do you know what the image is? Your visual cortex sort of does a neural network type thing to figure out, okay, I've seen dogs before, so how are we going to do this? Okay, well, this image has these colors and these shapes, and so I know with these colors and these shapes that it's this dog, and I know that's dog. And now that I've seen this unique dog, I'm going to add it to my training set, and now I have a better understanding of what a dog is. And that's exactly what your brain is doing constantly all the time. It's always trying to figure out new things about the world, so it has a better model on an outlook on how to interpret the world, which is brilliant, right? It's amazing. And so this is sort of just a mapping of the brain. So the blue here sort of signifies the occipital lobe, and here's the frontal lobe, obviously. So let's scroll down and talk about some papers. So here's an overview paper on how supervised machine learning is used in neuroscience. This is about more soc and psych, about like different demographics and factors that machine learning algorithms have been fed in supervised learning to find find what sort of groups and demographics are the highest risk of suicide. This is a paper that might have been covered already in the podcast on how machine learning can actually objectively, right, not through the eyes of a human, but objectively define what a mouse behavior is, what animal behavior is, and predict it to some degree, which is extremely exciting. I did not know before reading this paper that ML had come that far. And then here's what I talked about earlier about MRI imaging. So at the base of this is really just math, right? It's probability statistics, linear algebra, and intro calculus. That's like where you want to start if you want to get into this sort of research. If you want to email a professor and say, hey, look, I had these probability classes under my belt. So probability and statistics, that's used a lot, for example, in the neural networks, right? So each of those neurons have a certain weight associated with them that increases or decreases the probability of it contributing to a positive outcome, meaning a higher probability of success. And then linear algebra, so that's probability in linear algebra, and intro calculus sort of ready for probability and statistics, as well as get you used to some sort of mathematical notation, which is very important for reading like new math and new work. So which courses at Rutgers gives a comprehensive intro to math that's used in machine learning? So it's a little hard to read here, but the introductory math classes that are shown here are Intro Calc, so that's Calc 151, 152, Calc 3, which is multivariable calculus, that's 251. Differential equations isn't as important, 252, but if you're a math major or double major, you have to take it. And then you have 477 and 481, which is your intro probability and intro statistics. Well, it's not intro, it's, I would say, pretty comprehensive. There's also 478, which is stochastic processes, which is pretty advanced too and very difficult, but for sure useful. So as a neuroscience major or CBN major, like, are you going to use this? Well, most likely. That's what the data says. Machine learning has been increasing in prominence amongst papers and journals for some time now. It seems to be exponential growth, at least between this 10-year period. And so I hope you guys, especially the more mathematically oriented people, will consider this, learn more about it, use it in your work, ask your professors about it, use it as a talking point. You never know how that's going to sort of set you up and introduce you to people who maybe you didn't consider working with before. So these are some references. This is a great course on machine learning by a professor from Stanford. It's pretty much like the gold standard for getting into machine learning. These are some of the references. This is a YouTube video, right? I think the channel's 3 Blue Brown 1. Very comprehensive guide into neural networks. So with that, I'll conclude the educational segment. And remember, guys, you've got potential. Thanks for watching the talk on machine learning today.